It'll help us switch between Fourier space and real space. The fast Fourier transform is an algorithm that's really efficient and can simplify, for example, simulations that take days and weeks can be reduced to just minutes and seconds. And the FFT algorithm is efficiently evaluates the discrete Fourier transform, which is right below. It looks like the integral, except it's written as sums. And pretty much a general overview of it is it has bit reversing, which if you have an initial array, you take the indices and write the binary representation of them, and then flip them. That gives you and then you rearrange. You flip them, and that gives you a new array. And then that array is then, using the butterfly method, a special way of regrouping the elements of the new array. And after some point, you'll get back to the array of size n. And that will be the transformation of the original array. And because the fast Fourier transform can't do an infinite domain, we can take advantage of the periodicity. And so we can simulate in a square cell and replicate it many times over the entire surface. And we adopted the FFT algorithm from numeric recipes in C++. So we aren't only just simulating patterns, but we're also going to add in temperature effects. So these are all based off experimental results. The excess energy G, also the mixing term, decreases as temperature increases. So as temperature increases, it becomes more ideal mixing, so it becomes homogenized. Young's modulus E, which is the stiffness of the substrate, also decreases linearly as temperature increases, which is pretty obvious. If you have like a metal bar and you heat it up, it gradually gets, you can bend it.
Malleable.
Yeah, malleable. And then the diffusion coefficient, which was m in the previous equation, increases exponentially, which is also obvious because as temperature increases, chemicals tend to diffuse more. And so, also for the temperature in our paper, we have certain equations, and we show how we modify them. Software architecture. Initially, the user inputs data, and that data goes to displaying the initial concentration. And then the user can input the number of time steps he wants to simulate, and then can click simulate. And the calculations are done right in the calculation, the yellow square. We are given an initial concentration C, and we can use that to calculate P in real space. And then we use the FFT to transform both of them to the Fourier space. And using those, we can calculate Cn plus 1. And then to keep on, if you're not done calculating time steps, you can keep on going by transforming Cn plus 1 back to real space, and then making that original Cn the next time step, and then redoing the calculation and calculate the next time step. And then once it's done, you can show the next, after, let's say, 100 time steps, you can show what comes out after 100 time steps. And so here's something, we're going to show a few examples of our simulation. Here's one that this is homogeneous. So initially, it was a uniform concentration, around maybe 0.4, 0.5 on a scale of 0 to 1. And generally, they form serpentine stripes. And the bottom is an experimental result done by Plas et al. And this is these are more homogeneous simulations. What has been observed is that as concentration increases, the patterns start from quantum dots and gradually go to serpentine stripes, and then finally they reach quantum pits, which is the opposite of quantum dots. And the black images are more experimental results done by the same person, and they look really similar. If you notice in the experimental results, the white is actually the concentration. So, so each white dot, let's say in a quantum dot one, is a black dot in our simulation.
So we also did some models starting with like a heterogeneous initial concentration. So this one started as this circle thing, and then as it progressed, it reached this sort of like target. And one use for these nanoscale patterns is for making circuitry, so like wires. So we started out and we did one that kind of looked like wires, and you could see that it stayed, created these wires that would be good for transferring electricity nice and straight. And
also heterogeneous simulations, you can put a circuit on there, and then you can see how it's going to fall apart if it does.
At certain temperatures. And then this one we started with the triangle, and this one we started with these like three diagonal lines. Here we looked at temperature differences, and starting from the right here, this is at a low temperature, middle, and then high. And as you can see, it gets more and more homogeneous. This is little tiny dots, medium dots, and then like just big, huge splotches. And that backs up our model.
The first picture starts at 300 Kelvin,
yeah.
And the last picture goes to 500 Kelvin. And so this is a kind of an animated simulation. So this is what it is initially. After 300 time steps, it's slowly starting to break up into lines. We ran another 400 time steps, and it's starting to you can start seeing the lines now. And at this point, we can see that it's starting to form lines, like the picture we showed before. Okay, because we're solving these equations numerically, we have to ensure that we aren't getting a whole bunch of numeric error. And by trial and error, we found that time step around 0.0001 and 0.001 are the best. That if you could go lower, but the problem with that is that you have to run a whole bunch of time steps in order to get somewhere. And here, the top picture is 0.001. We've ran many simulations around that, like 0.00001 with 4 zeros, and they all converge to the same thing. But if we make it go above 0.001, like maybe 0.01, like this one, the second image, we can see that there's a lot of numeric error introduced. And if we were to continue the simulation, it would start doing really strange things.
Could you explain something about this? The species 1 and species 2, those appear to be the same picture. Are they? Or?
No, it's two different. It's two different chemicals on the substrate. So how they grouped their.
So does that say species 1 and species 2 are grouping in the same place?
Yeah, they tend, like many times, they tend to combine, react together.